Welcome to session 8 of real analysis. So far we were discussing the inequalities and various properties of real numbers like the order properties and algebraic properties of R. In today's session we will be discussing more about the absolute value and modulus and how these values help us in solving some of the inequalities. So, let us see the first definition. The absolute value of a real number denoted by modulus A is defined as mod A is equal to the number A itself if A is a positive real number, 0 if A is equal to 0 and negative A if A is less than 0. So, the concept of absolute value or modulus is nothing but the distance from the origin or distance from 0. So, we can see that the real number system can be arranged on a straight line where you have 0 in the middle, all the positive real numbers to be on the right side of zeros. That means, here you have 1, 2, in between you have all the real numbers between 0 and 1, between 1 and 2 and likewise. And on this side you have the negative real numbers, namely negative 1, negative 2, negative half is somewhere here, you have positive half here and so on. So, this sort of arrangement is there for real numbers, and for any real number on the positive side of the real number system, that is for greater than 0, the distance from 0 is exactly equal to that number itself. That is how we are arranging the real numbers. Say for example, modulus of 1 is nothing but 1, modulus of 10 is equal to 10 itself, modulus of 3 by 4 is 3 by 4. So, that means it is nothing but the distance from the point 0 or distance from the real number 0. The distance towards the positive side is exactly equal to that number. And on the other hand, the distance to the negative side is nothing but, if you have to find the modulus of negative 10, we can see that if you have 10 somewhere here, you have negative 10 exactly at the same distance towards the left side of 0. So, the distance is nothing but 10 itself, because distance cannot be taken as a negative value. That is why we are defining the modulus as mod A is equal to A itself if A is greater than 0, negative A if A is negative, A is less than 0, then only this becomes a positive value, and 0 if A is equal to 0, because 0 is at a distance of 0 from 0 itself. So, we can see in effect that modulus of A is always a positive number, because it is the distance from the point 0. So, that is the definition of modulus, and with that definition we can have the following theorem, where we have modulus of AB is equal to mod A into mod B for all the real numbers A and B, mod A square is equal to A square for any real number A. If C is positive or non-negative real number, mod A less than or equal to C is equivalent to writing minus C less than or equal to A less than or equal to C. And we have another result, negative of mod A is less than or equal to A less than or equal to mod A for all the real numbers A in R. So, let us see the proof of each of these results one by one. So, the first result says that, so we are going to the proof of the first one. The first result, modulus of AB is nothing but mod A into mod B. So, suppose either A or B is equal to 0, then this is equal to 0. So, let us consider the case where A and B are both non-zeros. So, we are taking the case where A not equal to 0 as well as B not equal to 0, because if either of them are equal to 0, this side is equal to 0 as well as this side is equal to 0, we will be getting the proof done. So, we are considering without loss of generality that A and B are both non-zero real numbers. Then by the law of trichotomy, we have the first case, if A is greater than 0 as well as B is greater than 0, what happens? If both A and B are greater than 0, then modulus of AB is nothing but AB by definition, because if A is greater than 0 and B is greater than 0, then by the definition of positive real numbers we have learned in the previous sessions, if A is positive and B is positive, the product is also positive. So, AB is greater than 0. So, by the definition of modulus, we have mod AB is equal to AB. So, we have this is equal to mod A into mod B, because both are greater than 0. Mod A is nothing but A, mod B is nothing but B. So, we are done. So, the first case is over. Case 2, if A is greater than 0 and B is less than 0, let us see what happens in this case. So, if one of the real numbers is positive, this shows that we have seen in the previous case that AB is less than 0. In one of the previous sessions that we have already studied, we have seen this result. If one of the real numbers is negative, then the product is negative. So, mod A happens to be equal to A, mod B happens to be equal to negative B, because A is positive and B is negative, and AB, since it is less than 0, what is modulus of AB? This is nothing but negative of AB, and that can be written as A into negative B, and which is exactly equal to mod A into mod B. Therefore, we have mod AB is equal to mod A into mod B in this case as well. So, the case 2 is also proved. Case 3 is A is negative and B is positive, which is exactly same as this case, just we have to interchange A and B, that is all. And if both A and B are less than 0 also, AB will be negative, and therefore, modulus of AB will be, sorry, both if A is less than 0 and B is less than 0, AB is positive, and so modulus of AB is equal to AB, which is equal to modulus of A into modulus of B, because it is negative. AB can be written as, the last case is something like this, if A is less than 0 and B is less than 0, what we have is AB is positive, therefore, mod AB is equal to AB, and this can be written as negative A into negative B, which is equal to modulus of A into modulus of B, because the two negative signs multiplied will become a positive sign. So, here also we are done. So, that is the last case. So, we have dealt with all the 4 different cases of different values of A and B, and we have seen that in all the cases this condition holds. Now, looking back to the theorem, the second statement is modulus of A square is equal to A square for all A belonging to R. So, that is simply by replacing this number B with A itself. So, that follows from the condition number 1, where we replace B by A itself. So, we have A square is equal to modulus of A into A, that is equal to. So, let us see the proof once more. So, second case we are going to see modulus of A the whole square is equal to A square. So, let us consider the case where A equal to 0, then definitely this condition holds, both equal to 0, both side, both LHS and RHS is equal to 0. So, proof is done. So, we consider the case when A is positive. So, if A is positive, A square is positive. Therefore, we have a square is equal to mod a the whole square, because mod a is nothing but a itself, because we have mod a is equal to a itself. And third case, when a is less than 0, we have mod a is equal to negative a. Therefore, mod a the whole square is equal to negative a into negative a, which is equal to a square itself. So, in all the different cases, we have a square is equal to modulus of a the whole square. So, we are done in the second case as well. The third case is, if c is greater than or equal to 0, then mod a is less than or equal to c if and only if minus c less than or equal to a less than or equal to c. So, let us see the proof of the third result. So, we have modulus of a given to be less than or equal to c. So, by the definition of modulus of a can be either a or minus a or 0. So, if a is equal to 0, there is nothing to prove, because it is already given that c is greater than or equal to 0. So, there is nothing to prove. So, we consider the other two cases where modulus of a is equal to a or modulus of a is equal to negative a. Negative a. So, consider the case when modulus of a is equal to a. Then what do we have? A is less than or equal to c. If modulus of a is equal to negative a, what do we have? Negative a is less than or equal to c. Therefore, combining these two, what do we have is, this negative a less than or equal to c means it is a greater than or equal to negative c. Because we are multiplying throughout with a negative number, we are getting the inequality getting reversed. So, a is greater than or equal to c. So, what is the union of these two? A is greater than or equal to negative c, union a is less than or equal to c, which indicates that minus c is less than or equal to a less than or equal to c. So, we have seen such examples in the previous sessions. We have minus c less than or equal to a less than or equal to c. So, if this condition is satisfied, we can retract and show that modulus of a is less than or equal to c. So, whenever you have modulus of a less than or equal to a positive real number, we can have negative c less than or equal to a less than or equal to c equivalent condition. And the last case is just followed from the third one by replacing c by the positive number mod a, because here the third condition is a more general form, because we need only c to be a non-negative real number, and here you have c is equal to mod a, which is strictly greater than 0. So, minus mod a is less than or equal to a less than or equal to mod a follows from the third condition. So, that is the proof of the theorem. Now, we shall look at the next important theorem, which is known as the triangle inequality, which states that if a and b are both real numbers, then modulus of a plus b is less than or equal to mod a plus mod b. So, let us start this proof by this previous theorem. In the previous theorem, we had the last condition that we are going to prove the triangle inequality. Triangle inequality. By the previous theorem, the last condition was negative of mod a less than or equal to a is less than or equal to modulus of a for some real number a. Similarly, you can name this as inequality number 1. Similarly, an equivalent result holds for the real number b as well. So, negative mod b is less than or equal to b less than or equal to mod b. You can name it as inequality number 2. So, you add both these inequalities. So, you have on the left side negative of mod a plus mod b is less than or equal to A plus B less than or equal to mod A plus mod B. Now, look at this inequality and go back to the previous theorem. What does this inequality now have? Negative of a number, positive number, is less than or equal to A plus B less than or equal to that positive number. So, by the condition number 3, what is this indicating? Modulus of A plus B is less than or equal to C, where C is nothing but mod A plus mod B. So, this is less than or equal to mod A plus mod B, and hence we have the proof of triangle inequality. So, that is this theorem. Now, we can see a corollary of triangle inequality where we have two real numbers A and B, then the absolute value of mod A minus mod B is less than or equal to modulus of A minus B, and modulus of A minus B is less than or equal to mod A plus mod B. So, let us look at the first result. So, we are going to prove the absolute value of, we are going to prove the corollary. The absolute value of mod A minus mod B is less than or equal to modulus of A minus B, is less than or equal to modulus of A minus B. So, let us begin with a real number A. How we can express this A? We can write this A as A minus B plus B, because what we have in the right side is A difference B, and that is why we want to write A in terms of A minus B. So, we have A is equal to A minus B plus B. Therefore, modulus of A is nothing but modulus of A minus B plus B. Taking this as one real number and B as the second real number, by triangle inequality, we have this is less than or equal to modulus of A minus B plus modulus of B. From where did it follow? It followed from triangle inequality. That is why this is a corollary of triangle inequality. So, corollary means something which follows from a theorem. So, we have, taking mod B to the left side, we do have mod A minus mod B is less than or equal to, this is less than or equal to modulus of A minus B. Name it as inequality number 1. Then, starting with the number B on the other side, we have B is equal to B minus A plus A. Again, we want to express B in terms of A minus B or B minus A. Again, applying the same result, modulus of B is equal to modulus of B minus A plus modulus of A. Therefore, modulus of B minus modulus of A is less than or equal to, by applying triangle inequality, is less than or equal to modulus of B minus A, or modulus of B minus A is same as what? Modulus of A minus B. Now, what does this result say? This says that if you take a negative sign out, you have mod A minus mod B is less than or equal to modulus of A minus B. Therefore, combining the two results, what do we have is modulus of negative of, what do we have? Negative of modulus of A minus modulus of B is less than or equal to modulus of A minus B, and in the previous case what do we have? Modulus of A minus modulus of B is less than or equal to A minus B. So, we have, this indicates that modulus of A minus modulus of B is greater than or equal to negative of modulus of A minus B. By taking the negative throughout, multiplying with a negative, we are getting this inequality getting reversed. So, we have now is negative of modulus of A minus B is less than or equal to modulus of A minus modulus of B is less than or equal to modulus of A minus B. So, we have seen in the previous case, if we have negative C less than or equal to A less than or equal to C, this is equivalent to writing the expression that modulus of A is less than or equal to C. So, what is in place of C here? We have C equal to modulus of A minus B, and instead of A, what do we have? Mod A minus mod B. Therefore, by applying in this result, we have modulus of A minus modulus of B is less than or equal to modulus of A minus B. So, that completes the proof. And the last part was modulus of A minus B is less than or equal to mod A plus mod B. This follows directly from the triangle inequality, where we have modulus of A plus B is less than or equal to mod A plus mod B. It follows from the triangle inequality, and replacing this B by negative B, what do we have? Modulus of A plus negative B is less than or equal to mod A plus modulus of negative B, and A plus negative B is nothing but A minus B. Then we have modulus of A minus B is less than or equal to modulus of A plus modulus of minus B is same as modulus of B, and therefore, we have this result being hold. So, that completes the proof of this theorem. Modulus of A minus B is less than or equal to mod A plus mod B. That completes the proof of this corollary. Now, as an example, we can see, determine the set A of all those real numbers x such that modulus of 2x plus 3 is less than 7. So, let us look at this question and we shall see the solution. We need to find A is equal to the set of all real numbers for which modulus of 2x plus 3 is less than 7. 2x plus 3 is less than 7. So, let us see how we can apply the theory that we have been discussing so far to do the practical problems or to find the solution of problems. So, just now we have seen a result, modulus of A is less than or equal to C is equivalent to writing negative C less than A less than C, less than or equal to A less than or equal to C. Now, you look at the question given. We are given modulus of 2x plus 3 is less than 7. So, how can we write this in an equivalent condition or equivalent inequality? We can replace this by negative 7 less than or equal to, or it is strictly less than, because we are not given less than or equal to. So, we can write it strictly less than 2x plus 3 is less than 7. 2x plus 3 is less than 7. So, we have adding a 7 throughout or adding a negative 3 throughout, because we need to find the x values. So, we can add a negative 3 throughout. So, we will be getting minus 7 minus 3 is less than 2x is less than 7 minus 3. So, that is negative 10 is less than 2x less than 4, and dividing throughout by 2 being a positive quantity does not change the inequality. So, we have negative 5 less than x less than 2. So, the set of all x values satisfying that inequality is nothing but open interval negative 5 up to 2. So, this is the final solution. So, that is how we can apply the theory modulus of A less than or equal to C in solving problems. Now, we can move on to the definition of a neighborhood, or in precise an epsilon neighborhood of any real number A. So, if A is a real number and epsilon is some positive quantity, we can define a set V epsilon of A is equal to the set of all those real numbers which are having a modulus value modulus of x minus A is less than epsilon, and x belongs to V epsilon of A is equivalent to writing negative epsilon less than x minus A less than epsilon. Why? Because we have defined modulus of x minus A is less than epsilon, applying the just previous result that we were discussing so far, mod A less than or equal to C. We can expand it as negative epsilon less than x minus A less than epsilon, and so adding an A throughout, the set of all those values x which are in the epsilon neighborhood of A is nothing but A minus epsilon less than x less than A plus epsilon. So, see how beautifully we have defined an epsilon neighborhood of the set of all real numbers. We have been discussing that real numbers actually lies on a line. So, whenever you have a real number say A, we need to find which is the epsilon neighborhood. Say epsilon may be equal to say half. You can take whatever be the value of epsilon that you wish to take, because we are discussing about neighborhood, it should not go beyond 1. So, our epsilon should be restricted somewhere between 0 to 1. So, usually because we are discussing about the neighborhood, we do not want epsilon to be more than 1. So, epsilon is equal to half if you are taking. There are only two options for the real numbers to exist on a real line near A at a distance maximum half apart, that is either it can be somewhere up to A plus half somewhere in this region, or it can be somewhere in this region. It is A minus half. It should be A minus half, A minus half. So, it can be either somewhere here or it can be somewhere here. So, maximum distance from A is expected to be half. That is why we restrict all those x values which are to be at a distance from A to be less than this epsilon. So, we write generally modulus of x minus A is less than epsilon. So, that this becomes A minus epsilon on the left and the right side becomes A plus epsilon. So, x belongs to the open interval A minus epsilon, A plus epsilon. So, that is what is called the epsilon neighborhood of the point A. So, that is the precise definition. Then we have a theorem which states that if A is a real number, if x belongs to the epsilon neighborhood V epsilon of A for every positive epsilon greater than 0, then x has no other alternative, x has to be equal to A. So, this is something similar to the result that we have discussed in one of the previous sessions, which was if you have 0 less than or equal to A less than epsilon for every epsilon greater than 0, then A has to be squeezed to A equal to 0, because A does not have any other option than to go back to 0. We have already proved this result. So, this is something similar to that. if x belongs to the neighborhood V epsilon of A for every epsilon greater than 0, then x has to be equal to A. So, let us look at the proof of this. The proof is something like this. We are given x belongs to V epsilon of A for every epsilon greater than 0. So, by definition of V epsilon of A, we know x belongs to the open interval A minus epsilon A plus epsilon. So, what does this indicate? Negative epsilon is less than x minus A is less than epsilon. Or in other words, by the previous result that we have studied, this is equivalent to modulus of x minus A is less than epsilon. And definitely modulus of x minus A is always positive. Therefore, we have 0 less than or equal to modulus of x minus A is less than epsilon, and this is true for every epsilon greater than 0. So, we are now in a condition to apply this result that we already know, but instead of A, here what do we have? Modulus of x minus A. So, this forces modulus of x minus A to be equal to 0. And when is modulus of a real number equal to 0? When the real number is equal to 0 by the definition of modulus. So, that shows that x minus A is equal to 0. So, that is why we have the result. If x belongs to the neighborhood V epsilon of A for every epsilon greater than 0, then x has to be equal to 0. So far we were discussing about the absolute values and modulus of real numbers, and now we have seen whenever x belongs to an epsilon neighborhood of A for every epsilon greater than 0, then that element has to be equal to that real number itself. So, these were the results of modulus and absolute values. Thank you.